Hello everyone, welcome to my class. Today I'm going to cover line integrals. So first let me give you a quick preview. So far we have integrated over intervals with a single integral, integrated over areas, 2D regions with double integrals, we integrate over volume, 3D regions with triple integrals. Now we want to integrate over a curve. That curve either is space curve or its projection on the plane and the plane curve, and we call that integral line integrals. And the line integral of a vector field plays a crucial role in vector calculus, as most of the big theorems of vector calculus involve the line integrals of vector field. So let me start with the definitions. Let me scroll down. Let's make small. Yeah, that's better. To here. Just I do by side here, so that it's easier for you to compare. So there are two types of line integrals we studied. So two types. One I call ds type for a scalar function f. Another one is this is vector, dr type for vector field. The template is fxyz ds over a space curve c. Or if you only take for function of two variables, then you drop out the z, then this c will be plane curve. Let me explain first the ds type line integrals for scalar functions, and then I'll talk about the dr, where r is vector, dr type vector field. Dr type line integrals for vector field. So let me talk to the first ds type. So here it is either space curve or plane curve needs to be parameterized or in vector form. So say it is parameterized by the t, so whose equation is given by rt equals to xt, yt, zt, t between a and b. Let me zoom in and then we talk about first the ds type. So for arc length function s, the derivative of arc length with respect to t is simply the speed. That means r prime t magnitude. We talked this in our previous classes in chapter, I believe, 13. And now, so ds equals to the magnitude of r prime t times dt, where r prime t is under the radical dx over dt outside square plus dy over dt outside square plus dz over dt outside square times dt. Hence, the line integrals of f with respect to arc length ds equals to a to b f of rt times ds is simply magnitude of r prime t dt. So we use either this formula or by converting this r prime t dt, or by substituting this value here. It's a to b fx t y t zt under the radical dx over dt outside square plus dy over dt outside square plus dz over dt outside square times dt. And for 2D case, just drop out the z variables. Now let me go towards the dr type line integrals. So again, our curve is here, rt equals to xt, yt, zt, t between a and b. And we know the derivative of r with respect to t is simply r prime t. And also we know the unit tangent vector is velocity divided by its magnitude. The first derivative of r divided by its magnitude is the unit tangent vector. And ds equals to r prime t dt. So this is coming from here. So ds equals to magnitude of r prime t dt. Let me scroll back. Yeah. So then the line integrals of vector field, this is the f dot dr equals to, this is the integral over curve c. So the integrals over c, f rt dot dr is r prime t dt. So we use this formula. And also this line integral of vector field, it represents the work done. So we are also using these line integrals to compute the work done by the vector field or the vector force. Alternative form of this line integral is, since vector field has components, let's say P, Q, R, and we know dr equals to r prime t dt, which is same as dx comma dy comma dz, and then take their dot product. So the line integrals of f over c, this dot dr, equals to, this is the line integral over c, so p times dx plus q times dy plus r times dz. So we took the dot product, we multiplied the corresponding component and then add them. So p dx plus q dy plus r dz integral over c. Now this is called the line integral in differential form. Okay, great. And the line integral with respect to x and y is given down here. So now let me zoom out. Yep. Quick side note. The curve C denotes the curve, if C denotes the curve AB, here, AB, traverses from A to B, and minus C denotes the curve in opposite directions, then the line integrals of scalar functions over negative C, means opposite direction of this means from going from now BA, minus is this going from B to A, is simply line integrals of f over c ds. Here the arc length doesn't change, so that's why this minus has no effect on our result. But in the vector field, integrating, or the line integrals of vector field f over negative c gives us negative, and then the line integral of f dot dr, which is due to the unit tangent vector, which changes the directions. Great. So now let's move on. Let me scroll down. So now we are ready for the example. So let's start example 1. Evaluate the line integrals over c of xy squared ds, where c is the right half of the unit circle, x squared plus y squared equals to 1. So solution, the very first step, our curve needs to be parameterized. So let's parameterize our unit circle. We know x equals to, put x equals to cosine t, y equals to sine t, and only right half of the unit circle. So our this t goes from negative pi over 2 to positive pi over 2. Then our curve rt equals to, whose equation is rt equals to xt, yt, so cosine t, sine t, and take its derivative. So cosine t derivative with respect to t is negative sine t. Derivative of sine t is cosine t, and take its magnitude, which is under the radical, the first component square plus second component square under the radical. We know from trigonometry identity, sine squared t plus cosine squared t 1, under the radical 1 is just 1. Then let's evaluate. This is the given line integrals equals to, now all in terms of t, so negative pi over 2 to positive pi over 2, and then x is cosine t, y is sine t, so squared is sine squared t, and then r prime t is 1, and dt. Since this function, I use the even property, the function is even, so I can only go 2 times integration 0 to pi over 2. I copy the integrand function as it is. Let me scroll down. That's better. And this integral is a good candidate for u substitution. Put u equals to sine t. Its derivative du equals to cosine t dt. And also change the limit here. So at t equals to 0, sine 0 is 0. At t equals to pi over 2, sine pi over 2 is 1, so u is 1. So let's rewrite our t integrals to the u integrals. So 2 as it is. This integral is in the now u integrals with u bounds 0 to 1. Sine is square t, sine t equals to u, so u is square. Then cosine t times dt is simply du. Cosine t dt is simply du. Then the next step, 2 as it is, integration of u square with respect to du becomes u cubed over 3. So 2/3 u cubed, put 0 to 1, put u equals to 1, that gives you a 2/3. Great. We finished this and this example 1. Let's move on. Let me scroll down. Move on. Yeah. So evaluate the line integrals of xy over c. So ds. C is a line segment joining 1, 0 to 3, negative 1. So the line segment is, let's sketch here, 1, 0 to 3, negative 1, 1, 2, 3, negative 1. So now we need to parameterize the curve. Now here's the line segment, and we know from chapter 12 the parametric equation of a line is x equals to x0 plus at, y equals to y0 plus bt, where t varies from 0 to 1, and a and b are the constants given by a equals to x1 minus x0, and b equals to y1 minus y0. So x equals to x0 starting from 1, 0, so this is your x0, y0. So 1 plus 3 minus 1 is 2t, so 1 plus 2t, y equals to 0, then plus b is minus 1 minus 0, so minus 1, so minus 1t, which is simply minus t. Then take its derivative, dx over dt is 2, dy over dt is minus 1. Hence our line integrals becomes line integral of xy over c with respect to ds equals to integration over t equals 0 to 1. And then here, so x is 1 plus 2t, y minus t under the radical. So the derivative of x with respect to t square, so 2 square, plus the derivative of y with respect to t square, negative 1 square, times dt. Then this constant, this under the radical is 2 to 4 plus 1 5 under root of 5 means radical 5, pull outside, and then this minus also pull outside, and the integral is 0 to 1. Then you foil this t inside, so minus, sorry, I already put minus outside, so t times 1 t, t times 2t, 2t square dt. Let me zoom in here. Yep, this is more better here. Yep. Then the integration of t is simply t square over 2. Integration of 2t square is 2t cubed over 3. Put t bounds and simplify. This gives you negative 7/6 radical 5. Awesome. Let's move on. Let's do another example 3. Now let me maybe make 170. That's better. Yep. So here. Evaluate the line integrals denoted by I equals to line integral over c, z squared dx plus x squared dy plus y squared dz, where c is a line segment joining the point in the space 1, 0, 0 to 4, 1, 2. Again, our c needs to be parameterized. So x equals to 1 plus 4 minus 1, 3, so 3t. Y equals to simply t, z equals to 2t. T goes from 0 to 1, take the derivative of x, y, z, which gives you dx equals to 3 dt, dy equals to dt, dz equals to 2 dt. Then hence, our line integrals, I equals to integration over 0, 1, z squared 2t squared times dx, dx is 3 dt, and x squared is 1 plus 3t squared times dy is dt, plus y squared, y is t, t squared, times dz, 2 dt. Great. Then this 2t squared becomes 4t squared, and you foil 1 plus 3t outside square is 1 plus 6t plus 9t squared, and you factor the dt out, and you add and subtract here. There's no subtraction, all addition only, so simplify, it gives you this t integral, and integrate with respect to t. That's easy to integrate here. Then plug the value t equals 0 to 1, which gives you 35 over 3. Great. So let's move on. Let's do another example. Let me scroll down. Now let's do example related to vector line integrals. The previous example was the line integral of scalar functions or scalar field. So the example 4, evaluate the line integrals I equals to line integrals O over C. I forgot to put the C here, over C of f dot dr, where f equals to sine x cosine y x z, and the curve is given as rt equals to t cubed minus comma minus t square comma t between 0 to 1. So then by formula, the line integral of vector field f equals to integration over c f of t, oh that's a rt, f of rt dot r prime t dt. So this equals to, so the t bounds are 0 to 1. So f of rt is sine x is t cubed, so sine t cubed. Cosine y is minus t square, so cosine minus t square. xz, this is x, this is y, this is z, so x times z is t to the power 4 dot r prime t is the derivative of rt, which is 3t square minus 2t 1 dt. Write down the integral 0 to 1 as it is and take the dot product between these two vectors. We multiply the corresponding components and add them. So 3t squared times sine t cubed, and we know the cosine functions, the identity cosine minus theta becomes simply positive cosine theta, so this minus disappears, so only this minus is there, so minus 2t times cosine t squared plus t to the power 4 times 1 is t to the power 4 dt. So let's evaluate these integrals of each terms here. So the first one is a good candidate for u sub, put u equals to t cube, whose derivative is d equals to 3t squared dt, then sine t cube simply becomes sine u, 3t squared dt is du, and then sine integration of sine u is negative cosine u, and you substitute the value u equals to t cube, then your result is negative cosine t cube. So I hope you understand this integration here. And then for the second one, also this is a good candidate for u sub, put u equals to t squared, then its derivative is d equals to 2t dt, so 2t dt will be du, this will be simply cosine u, integration of cosine u is sine u, and you substitute variables again, u equals to t square, so that is sine t square, and this minus is that minus, and plus t to the power 4, integration becomes t to the power 5 over 5, your limit goes from 0 to 1. Then put the t equals to upper limit, t equals to 1. So t equals to 1 is negative cosine 1 here, negative sine 1 here. T equals to 1 is 1/5. And put the lower limit, so minus, and put t equals 0. So t equals 0 gives you cosine 0, there is 1 minus, so I need to add them. So then cosine 0 is 1, so, and then rest are zeros. So 1 plus 1/5 is 6/5. Great. So let's move on. Let me scroll down. That's better. So example 5. Find a work done by the force field, where force field, which is a vector field, F equals to x squared comma y ex on a particle that moves along the parabola x equals to y squared plus 1 from point 10 to 21. So in this picture here, from 10 to 21. Great. So let's start the solution. So the very first step is we need to parameterize the curve. So let's parameterize this parabola. So the lucky variable to get t is y. So let's put y equals to t, then your x equals to t square plus 1. That's one way to parameterize this curve. Then clearly t between 0 and 1, because y equals to t, so y limits are 0 to 1, so t is 0 to 1. Then our parabola in parametric form is xt yt, so xt is t square plus 1, yt is t. Next step, take its derivative. R prime t equals to 2t comma 1, 2t1 comma 1. Hence, our work done equals to line integrals of vector field. So the f dot dr over c, so the integral over c, now this becomes integral over 0, 1. So then the f rt dot r prime t dt. Let me scroll down. That's better. Then I'm here. Okay. So then, oh, let's do this way. I want to see the vector field also. So then f is given as x squared. So now x is my t squared plus 1. So t squared plus 1 outside is square, comma, y times e to the x. So y is simply t times e to the power x is t squared plus 1. T squared plus 1. Great. And then this is the dot product. R prime t, we found here 2t comma 1, 2t comma 1 dt. So first, now let me scroll down more. Yeah. So then first, let's take a dot product between these two vectors. So multiply the corresponding components and add them. So which is here, which is a t integral over 0 to 1. And now in both of these terms, u sub, put u equals to t squared plus 1, its derivative is d to t dt, and then this simply u cubed over 3, u is t squared plus 1, so from the second one, simply e to the power 2t plus 1 over 2, and limit 0 to 1, so put the value t equals to 1, minus t equals to 0, simplify, this gives you 7/3 plus e squared over 2 minus e over 2. Great. Now now example 6 I assign as a classwork for you to work. So that we have a given vector field, we have a curve equations, and evaluate the line integrals. And then I think this is quite long, and in the next sections we will learn a fundamental theorem for line integrals. Then that saves our life. Using that theorems, the computation of these line integrals will be way easier than these methods. Okay? So thank you.